Hello everybody, my name is Dion Safi and my partner Jay Patil. We're doing a presentation on chapter 52, sports scheduling. So, an introduction on sports scheduling. Sports scheduling has been a problem since the 1970s of organizing team tournaments. Some examples that use sports scheduling is the Major League Baseball, National Football, or the NFL, the National Football League, uh, NBA and the National Basketball Association and other minor tournaments that take place in today's society usually use uh, um, scheduling problems. So there are different variation of the problems. One of the first variations is the single round robin tournament problem, which every team plays each other at least once. The second variation will be the double round robin tournament problem, which every team plays each other exactly twice. Um, there's the balanced tournament design problem, in which every team plays each other once. However, games played by a team are to be equally distributed by the only possible facilities. What does that mean? Um, it means that there's only a limited number of facilities, such as basketball courts, fields, or venues which these events or slots or games are allowed to take place. And the bipartite tournament problem, uh, with two teams of n players, each player must compete with every other player on the other teams. So those are the uh, these are some of the variation of problems with scheduling. So some terms that are to be introduced prior to um, moving forward with the presentation. Uh, One of the first terms that is introduced is a schedule, a map of games in slots or time periods where a team can play a game at most once. Mirrored is games played in the first half that can be repeated in the same order in the second half. Another variation of mirror is a partial mirror. Slots may mirror each other but not necessarily divided in half. What this means is you have, let's say, games 2 through 10, they will be mirroring the same games of uh, 40, 40 to 48, and you have a total of 50 games. So no, you have a total of 60 games. So what that, as it shows, they're not exactly in the same half, but they are partially mirrored. So a compact is a schedule that has a minimum number of slots. A pattern is a vector of home, away, bye games for a single team over a schedule. A pattern set is a collection of patterns. Complementary, a pattern that has one home and one away game. Tour is the schedule for a single team. A trip is a series of away games. Homestand is a series of home games. So one of the first problems we're going to talk about is the single round robin tournament problem. For the single round robin tournament problem, we first need to identify the number of teams. If there's an even number of teams, each team will be playing in every slot. If there is an odd number of teams, each team will be having one bye. For n number of teams, we are required to have n minus 1 slots. So, and our input will be a set of n teams where t equals 1 to n teams. And what we will get is the output of the mapping of the games set, where G equals G of ij, where G, lowercase g is the game, and I and j is the number of the team. Obviously, I and j are contained in the set of T, where I is less than j, is always less than j. Where the slots are in the set of Sk, and k is equal to 1 to n minus 1, and if n is even, you will have k, if n is even, you'll have k up to k equals n minus 1. If you have if you have odd number of teams, no, if you have an even number of teams, you'll have k equals up to n, such that no more than one game including I is mapped to any given slot for all the teams in T. So our second variation of a tournament problem is a double round robin tournament problem. The double round robin can be created by combining two single round robin tournament problems, and the second half will be a mirror version of the first half. The second half of the schedule repeat the games in order, however, reversing the venue. There may be an unfair pattern created within the schedule because some teams may be playing 3 consecutive away games. So as the single round robin tournament problem, we will have the same input of an n number of teams of t equals 1 to n. So the output will be the mapping of the games set G, where lowercase g of I for every game, and I and j is contained in the number of teams T, uppercase T, where I is less than j, where the slots in the set S equals sk, where k is up to twice the number of teams. So the main difference between this output and the single round robin output is the size difference of the number of slots that are created. And if n is even, it's n minus 1, and if n is odd, it's up to n, such that there's no more than one more game including I is mapped to any given slot for any teams in T. So one of the effective uses with the single round robin problem is using Latin squares. A Latin square is of order n, is an n times n array, which each cell of the array contains the element from the set S of 1 to n. To generate its fix the first row with any permutation of 1 to n, then enter the n minus 1 cycle permutation of the n integers in the remaining rows. Latin squares have a direct correlation to a single round robin problem. It allows it to generate the SRRT, which is also the single round robin tournament problem. However, we are only interested in the even number of teams because this can cause an odd number of teams that require a bye, which the Latin square is unable to produce. So now we're going to be talking about balanced tournament designs. As described, a balanced tournament design problem is where n number of teams play each other once, and there is an f number of facilities, as we talked about, number of fields, venues, or courts. So our input is going to be two different inputs. We're going to need a number of t, a set of t where t is a number of teams, and a number of facilities f. So to map this game, we're going to again put a set G, where G equals the set of the games of I and J, where I and J is contained in the set of teams, where I is always less than J. Then to the slots available at each facility described by the set, S will equal S Fk, where F equals 1 to F, and K equals 1 to N minus 1. And as the previous problems of the double and the single round robin, if k is even, we'll have n minus 1. If k is odd, we'll have n. So there will be no more than one game involving team I is assigned to a particular slot. The difference between the number of appearance of a team I at two separate facilities is no more than 1. So the fourth type of problem we'll be talking about is the bipartite tournaments problem. So this specific type of problem was where there was two different teams, and every player that was in the team will be playing the other players on the other team at least once. So we'll take two inputs, and there'll be the players, the n number of players of teams 1 and 2. As described, x of 1 to x of n is set of players in team 1, and y of 1 to yn is a set of players in team 2. Obviously noted the size of these teams should be the same. So the output will be a mapping of games where there's a set G, where G of ij, where I is contained in T1 and J is contained in the set of T2, where the slots will be set to SK, where K will equal to the number of teams on number of equal players on both sides of the team. One game including T is mapped to any given slot for all of T that is contained within the union of T1 and T2. So there's an example of a bipartite tournament. A balanced bipartite tournament is shown within chess. The player that uses the white piece has an advantage because the white player always goes first. As in the rules of chess, white goes first, and then whoever's the black playing the black side of the game, they will go second after white color. In order to make the tournament fair, each player would have to play white an equal amount of time. In each slot, each player would have to be using white while the other half will be using black. So as it talked about, to make it completely fair between all players and there's not a disadvantage of an assignments of white and black, one of the given one of the givens that we will be using is the fact that every player will be playing white at least once, and then not once, every player will play white an equal number of times as they'll be playing black. So the entries in A give the slots in which games are assigned, and the entries in B indicate which team plays white. Specifically, Aij equals K means that Xi plays Yj in slot K, and Bij even means that Xi plays white in the game against Yj, and Bij odd means that Xi plays black in the game against Yj. As I described earlier, where there has to be equal number of games for the white and black distribution for the game of chess. So now we will be discussing the graph algorithms that are used, and the variations of scheduling algorithms within this series. So the graph theoretical model for a single round robin tournament among two M teams is the complete graph of K2M. So an edge ij represents the game between team I and team J. A single round robin tournament can be presented in L factorization, where f1 up to f2m minus 1 of K2M, where each factor includes the game scheduled in one slot. An L factorization of K2M may also be understood as the coloring of K2M, or a decomposition of K2M into perfect matchings. The arc IJ represents a team game where it represents the game Team I at Team J, and the arc JI represents the game Team J at Team I. So minimum break problems within schedules. In an oriented coloring of K2M, there are at least 2M minus 2 breaks. What this means is, so within this graph, there is at least a number of break slots within within the graph. There are two possible patterns for a round robin tournament with two M teams that have no breaks. It's either the beginning with a home game or an away game. No pattern may be repeated in a feasible pattern set, thus all two patterns must have breaks. So another possible problem that will be used amongst the scheduling algorithm is the division games. There are leagues where teams play in different divisions. There will be where they would be divided into East, Central, West divisions, for example. This was an example provided by a book where it was talking about Major League Baseball. There's also other leagues such as football that they have not only the different conferences, but they have their four different divisions within each conference, such as the North, South, East, and West. Same goes with basketball. So our problem would be figuring out how to schedule the teams with different divisions and see how we can pair them together. We would want division games during the week, while games with other teams would be on the weekend. Two games are played a week with a total of two M teams. With each team with play two each team would play two M weekend games, and they'll play two M minus one weekday games. So to construct this, we would make a graph of two M nodes, which would cover weekday slots, and another graph of a bipartite graph where X equals Y equals 2M to cover the weekend slots. The schedule in total will have 4M minus 2 breaks within the schedule. The solution is dependent on having an even number of teams. Without one of these conditions, there is no known factorization for the weekdays. This result represents a significant departure from the results above in that it does not depend on the rearrangement of the canonical factorization. Now, Jay will continue the second half of the presentation.
Hi everyone. So let's see how can we solve source scheduling problem with integer programming and constant programming. An integer programming problem is a mathematical optimization or feasible program in which some or all the variables are restricted to be integers that takes only the numbers from 0, 1, 2 and so on till n. And we use decision variable in this to solve this problem. Decision variables can take only the integer values, and these are binaries and the integers. So binary variables can be a 0 to 1. So the example could be for who will play against who. That means team A is playing against team B, then those variables had to be 1 or 0. And another example could be assigning success to a shift. So one who is going to work in this shift. And integer variables can be 1 to n, and the numbers of teams, and example could be the number of teams playing in this tournament, and that is number of teams are going to be participating in this tournament for the scheduling. And another example, like the number of workers to assign for a particular shift. So those were the with those where we can use the integer variable. Next, decision variable. Here in decision variables are which team play against which team, yeah, and we need to decide which team plays each other in each week. So we define the variable xijk, where x I stand for team I and j are team names, and k is a slot. If I plays with team j in k slot, then that xijk is going to be 1, or else otherwise if the team is not playing in that slot, then the variable is set to 0. Example would be team A plays with team C in second week, then XAC is 1. That is team A and team C are playing in the second slot, so it's variable set to 1, and team A, team C in first slot they are not playing, so the variable set to 0, and so on the way. And this is a binary decision variable which can take only 0 and 1. Second one is formulation. So there is no objective for this basic single round robin tournament problem, SRRTP. It's feasible problem and of finding xijk that satisfies the following constants. So it's just a simple feasible problem to solve the xijk. And so first assignment says for every I and k in n-1 slots, each team plays exactly once in each slot. And second way expression says for every team j from 1 to n and I smaller than j ensures that they play exactly once with opponent team. So the constraints are like this. The first constraint guarantees that every team plays exactly once in each slot, and second ensures that each team plays with the other opponent exactly once. Let's see an example for that formulation. So let's assume we have 4 teams: team A, team B, team C, and team D, and constraint is every team plays exactly once in per week, and second constraint is each team plays every opponent exactly once. So the formula goes like this: xab1, ac1, and ad1. That is, team A is playing with B, C, D in first slot is going to be 1. That is, so that means team A is going to be playing in the first slot only once. Other two variables set to be 0. If team AB is playing in the first slot, then team AC and XAD are going to be 0. Similarly for the other teams as well for all 3 weeks. And the second constraint says xab1 plus xab2 xab3 equal to 1. That means the xab are going to be played only once in either of these 3 slots. So if AB are playing in first slot, then they are not going to play again in the second slot or third slot. So the variable is set to 0 in that case. So the next one is double round robin tournament problem. So let's see how we solve this. It's like a constraint programming. So why simple to express IP? This may not be easy to solve when more problems are added or more constraints are added in the problem. Like DRRTP includes a number of problem-specific constraints falling into 2 broad categories. The categories into 2 things. One is pattern set constraint, and the second one is team-specific constraint. So pattern set constraints include infeasible pattern sequences such as 3 consecutive home or away games, and equally distributed home weekends, away weekends, and home weekdays and away weekday games. That is, so the matches are going to be played in home or away in during weekends or weekday times, and those need to be distributed equally. And team specific constraints include fixed home and away pattern. like fixed game and opponent ordering constraint. These types of constraints are typically of the particular sports scheduling problem in the literature. So that means, so number of fixed home and fixed away matches pattern, like consecutive these many games should be in home, or consecutive these many games should be away, something like that. So yeah, so this will come under team specific constraint. So, and it's very common and practical to have good matches during the weekend. So objective of this problem is to maximize the good weekend slots. So we need to have good matches during the weekends, so to gain more popularity or something like this. Is a practical problem, like we need to have good matches during the weekends. So formulation for this goes like, in order to maximize the number of slots between games I at j and j at I, and possibly more importantly to simplify the problem using partial mirroring scheme. So game I is playing at j and j is playing at I, it could be easy to understand mirroring the earlier solved one, the solutions. To generate a set of problems, we follow this pattern. So like, let P be the set of patterns as we solve what are the patterns, and S be the set of slots. So S be the number of slots available during that match. And the binary variables are xi is 1 if pattern is selected and 0 otherwise. So if pattern is selected, if xi pattern is selected, then the variable is set to be 1, if not then 0. The coefficient hik is 1 if pattern I has some home slot k and 0 otherwise. If the match is going to be at home, then the variable is set to be 1 at that slot. And same as aik, where a stands for away, is 1 if the pattern has away game, and k slot is set to be at k slot is, and if it's not selected, then it's going to be a 0. Then so formula for this goes to, we need to minimize the number of patterns which satisfies this constraint, like ijk at the k slot where j is greater than I. That means they should be playing at least only one. There won't be a duplicate. So we need to minimize the pattern and select, and this substitute to hik xi equal to 4 for all k's, with all k is subset of S, and k again away equal to 4 where all k is subset of S. So yeah, this formula simplifies to minimize the pattern and equally distribute the home and away matches. So after optimizing the IP, a cut is added to prevent current solution from being regenerated. So we need to re-optimize the solution. If it's stuck or if it finds somewhere the bad pattern, then you need to be, the current solution needs to be stopped, and it need to be reanalyzed and continue the process and compute it. And this process continues until all patterns set with an objective value less than 2 are found. The objective of the value should be less than 2. Until then we need to repeat this process. So constraint program, second one is constraint programming. So constraint programming is a combinatorial approach to solve hard optimization problems that grew out of logic programming. It is same as previously discussed home and away match constraint. So Hens reported that the author Hens reported that The most effective search strategy seemed to be first enumerating the variables associated with the first slot and progressing it to those associated with the last slot. So first, he reported that first we need to enumerate all these variable and to assign it to first slot, then progress it to the last slots. And formulation is same as the IP. CP constraint programming algorithm naturally searches for all the feasible solutions, so there is no need to add cut and restart and optimization process as with IP. So it takes all infeasible solution at one step, so there's no need of cut and reanalyze optimization things. And the same way, the Hans reported that the most effective search strategy seemed to be first enumerating the variables associated with the first slot and progressing it to the associated with the last slot. To generate complete schedules from pattern sets, so Hans use the following approach to generate a schedule. Hans approach the following. Hence approach the following steps. So first what he did, he first assigned the team to pattern, then match teams in games. First assign the teams to each pattern, then match teams in the games. And a single CP model is able to accomplish these two steps. Or so the assigning to pattern and the match in the games team in the games are did in a single step. So although the set of variables matching teams and patterns is completely initiated before any choices are made for the variable that pair team into the game. So using CP model rather than enumerating and reversing the order of phases resulted in a great deal of run time saving. So this model saves a lot of time, and it could able to solve the problem in a few minutes, within 30 minutes, which could have been taken 24 hours in numeric approach, which is an IP programming. So now let's compare IP and CP programming. Where so as comparison model, for this comparison model, Trick presented a paper benchmarking the two methods on various types of SRRTPs and DRRTPs. So he compared these IP and CP models, and the Trick comparison resulted something like this. So he tested these two models with randomly generated forbidden games assignment created by Hans, and then he compared the performance of the basic IP and the standard CP formulation shown in the earlier slides. So IP performed better in randomly generated linear objective functions. No additional conditions required in single round robin transportation problem, whereas for CP it required additional constraint in order to complete this test. So we had to have extra constraint to complete this problem in constraint programming. So and it looks in IP it took very long time to process, as it needs to add, cut and re-optimize the models. So DRRTP perform better with pattern constraint limiting home and away matches. So CP perform better when you have more constraint and something like home and away matches. So it did perform well. So CP performed well in there, well if there is constraint in the problem, but there are no two approaches could solve the solution in 30 minutes for n equal to 10, that means 10 matches. So if there are 10 teams, they could not solve the solution within 30 minutes. So this increases exponentially with the team size increases. With strong IP was able to prove infeasible without branching for all these problems. So IP could able to solve this problem with a little less time compared to CP in terms of infeasible and without branching the things, without having more constraint. IP could able to solve this problem little quicker than the CP. So let's take an example to schedule a tournament with integer programming. So we have 4 teams, team A, team B, team C and team D, and we divide these 2 teams into 2 groups. Team A and team B in one group, team C and team D are going to be in another group. So there will be the constraint are there will be a tournament of 4 weeks, and play other team in a division twice. That means if in the same group teams are going to be twice with each other, and if in the other team they are going to be played only once, and play exactly one team each week. So each team should play only once in a 1 week. So these 3 are the constraints, and our objective is to maximize team preferences. So we need to get a more preferences out of this with this constraint. So we apply this constraint in a IP formulation. The constraints are the formula for constraint. So the formula for decision we'll see. Binary variable xij if 1 if playing match, or if 0 otherwise. So that means if team A, B are playing in slot 1, then the variable xab is set to 1, and in other slots xab are going to set to 0. In the same way for other matches as well, other teams as well. Like if team B and C are playing in the second slot, then team X, C, B and X, B, C are set to be 1 in the second slot, and other slots is going to be 0. And the formula of constraint are xab1, xab2, xab3, xab4. The sum of these 4 equal to 2. That means AB are in the same group, so they should play twice in 4 weeks. So in 4 slots, so this set to be 2. In the same way it goes with the C and D, where xcd1, xcd2, xcd3, xcd4 are set to be equal to 2. And second is satisfy the first constraint, and second constraint is xac1, xac2, xac3, xac4 equal to 1. That means team A should play with team C only once, and the same way we go to team A should play with team D only once in 4 slots, and other same thing for B, C and B D as well. And the third constraint is they should play only once in each slot. So if team A is playing in first slot, then they should not play in the other 2 slots. That means team AC and team AD are going to be 0. Similar constraint with every team in a week. And the objective is to xab1 plus 2 xab2. This is a combination problem, so the slot wise it increases like this. So if xab1 plus 2 xab2 plus 4 xab3 plus 8 xab4 plus xcd1 cd2 to 4 xcd3 8 xcd4. That means if xab1 is playing in the first slot, then that variable is set to the value, and if it's not playing in the third slot, that is 4xab3, then that's contribute a value to 0. So that way that is going to be like exponential. And finally the formula, applying all these rules, we get the solution in Excel. So I tried to solve that formula in Excel, and here is the solution. So I set all the variables like constraint A, team A is playing with team B twice, so we are set to be 2, and C is playing it 2 twice, and all other variables are set here. And finally, this is the solution we get with the solver plugin in Excel. So AB is playing in third and fourth week, and because they need to be played twice, and the same way like CD is going to be here, and yeah, this is the solution. So those two are actually taking time consuming. So uh, build propose with the heuristic approach. The heuristic approach, it could be find a good solution but not necessarily optimal ones. It could find a solution but not optimally, but you could get a quick solution for the problem. So how we propose the approach, we'll see. So Bean and Build rejected IP model approach to the problem because of its size and the time to solve this problem, and complexity increases and when added new constraint. So it again time consuming, reanalyze, and it's going to be complex and it's quite difficult to solve the problem and analyze it. So he rejected that IP approaches, and he came up with this solution for the steps. So the steps he followed are: first, greedily generate good trips with up to 5 away venues. First, greedily generate all the matches, all the trips where up to 5 away matches, and order the trips from greatest to smallest distance. So we have the longer distance first come should play first, and smaller one should play later, so that they will get time to relax or something. And then select the trip at the top of the queue. If possible, schedule it in a slot with the least stadium availability for the traveling team. If it is not possible to schedule the fourth, break it into 2 or more sub trips and insert these at the end of the queues. So if a very long distance, then we need to divide it and reassign it. So yeah, repeat this 3 steps. Repeat this third step until only a small number of trips remain in the queue. If there is until we need to repeat this steps until we get a small trips in a tournament. So use an IP after this. Use an IP to complete the schedule, minimizing traveling distance. So after all this assignment done for the trips, we need to use IP integer programming to complete the scheduling, minimizing traveling distance. And they reported that this approach was successfully used to schedule 2 seasons in NBA tournaments. So yeah, so next one is conclusion. So sports scheduling provides an interesting combination of practical application and theoretical challenges. There are a number of problem types in this area, and each has been attacked by a variety of solution methods. Even relatively small instances remain computationally challenging. So even small changes in the problem statement become challenges. So it's still an open problem, and it's very opportunity area, fruitful area for more research in this problem statement to solve this effectively.